Yeah. Okay, welcome everyone to this live session. Mm, I am Chandan Karfa, so the course instructor. I think students are still joining, so I'll probably wait for a couple of minutes so that student will join and then we can start discussing. So students are joining, right? Okay, okay. So I'll just wait for maybe a couple of minutes. Yeah. Yeah, I have seen that. So I'll discuss. So when I can just keep discussing even if the students is not here, right? So that they can see the recorded video as well. Hmm. Yeah, I think quite few questions, 10, 12 questions I can see. Okay. Hmm. Hmm. So welcome everyone again to this live session. We are into the sixth week of this course, and I hope you all uh, enjoying the course in the sense you are learning. It's a learning experience. So in this live session, it's a good opportunity for you to ask any questions that you have corresponding to this course, any doubt you have, right? Uh, uh, so there is one doubt from one somebody that there is no link of MS Teams, MS Team link to goes to YouTube. Um, I think our support team can help you. Please address this concern, our support team from NPTEL. Okay, so in this session, what I'm going to do is that feel free to ask any questions you have. It's a good opportunity for you to ask any questions from the technical part as well. You say, suppose you do not understand something in the video, or also if you have any associated questions, anything that is relevant for around in this course, right? I'll be happy to answer these questions. I'll be online for 1 hour at most, but if there is no questions, probably we may have to wind up the session early as well. So it all depends on your active participation, right? So to start with, what I'll do is I'm going to take the questions that I have already received from the student from on the form that has been shared with you all the learner by the NPTEL team. So in the meantime, I'll keep discussing the questions that I received from there. And then in the meantime, if I receive any questions from you in the chat, so feel free to chat, put your question in the YouTube chat as well as the Teams chat, whatever is your convenience. So where are you joined? So you can just put your questions there. So I'll just start with the questions that I have received um, in the Excel sheet. So first is Binoy Kumar. But he just no questions essentially. He just appreciate the course. So thank you, Vinay, for the appreciation. Hemant again, he has no questions essentially. Then I have Harshit Prajesh. He has a questions. The question is actually interesting question. Is What are the key difference between writing? Maybe I'll share my screen as well so that you can read the question as well. Yeah. So the question was asked by Harshit Prajesh is what are the key difference between writing Verilog code for simulation versus writing Verilog optimized for synthesis? What common pitfalls students should avoid? Yeah, it's a very good question. So if you just look into the Verilog, there are certain things which is not synthesizable at all, right? Um, what do you mean by synthesizable? In the sense when you try to use EDA tools to bring them into layout. So the first and foremost thing is that in simulation time, we may have some non-synthesizable uh, code in your implementation, but whenever this is fine for simulation, right? But whenever you try to synthesize them, it will give you error. So you should first point is that you should not have any non-synthesizable syntax in your code which has to be synthesized, right? Just to give some example, say for example, if I take the test cases that I have used in my course. So if you see here, this is the implementation of a decoder, right? Which is effectively just a combinational circuit where I have 8 outputs, and this is the corresponding expression, right? Where this X, Y, Z is our inputs, right? So this is synthesizable, right? So because there is no problem. But when you see the test cases, so test bench, what I'll do will effectively I'll give various combination of the input and see whether my output is correct or not, right? So here I am using this kind of syntax, right? After 10 unit of time, you flip the clock, right? And then what I'm doing here is that I apply some I after 20 seconds, I do I plus plus and then give I as the input, right? So this kind of signals are basically non-synthesizable, right? So you basically add this kind of um, time stall and all, right? So these are basically part of the simulation code, like say monitor and all those things. So so effectively mean you understand that there is a test bench and then you have the design, right? So in test bench you should use all this kind of time related code which basically sequentialize um, your design, right? So which you should not use in the synthesizable code, right? So that's the very high level thing. And some people sometimes just try to, I think the most common pitfall that students usually do, they don't think hardware as a parallel computing unit, right? So if you see if you have a very log code where you have say 4 adders, right? And there are some registers and all those things. So you have to understand that this 4 adder is happening in parallel in hardware. So every clock, all 4 will do 4 operations, 4 addition operations. uh, so now whether you want to use these 4 operations or not, it's your requirement, right? In one clock, maybe you want to use 2 adder. In the next clock, you want to use one of the adder. In one clock, you want to use 4 of them, right? So whether you want to use them or not, how do you control that? Is effectively you whatever the result is coming, whether you'll accept or ignore that, right? What do you mean by accept? Whatever the value is coming, it is going to some register. If you just put the enable of this register 0, that means disabled. Whatever computation happened there, it will not impact the output, right? So as a result, what will happen? Your that operation is actually ignored. So many time I have seen student to write code who basically think very like as a sequential code that I'll do this operation, then do this operations and all. But essentially in hardware, maybe all 4 operations is happening because he has instantiated 4 adders. But his objective is probably to use 1 adder in every clock. But he did not understand that he basically put 4 adders in his design. And when he sees simulation, he'll see completely different thing because he is basically all 4 is happening in R4 clock, and most of the operation is basically useless, right? So I think the major problem or the pitfall is that you have to visualize your hardware as a parallel computing system where your everything is running parallel, and it's not about executing the sequentially, and you have mindset of having a controller which effectively try to control what operation to accept, what to reject. right? I think answer your questions. Um, I think there are a few questions coming here. I'll probably do an interchange between this. I think there is Deep Sankar Jha. I think he has questions. Hi, Deep Sankar. Uh,
Hello,
so I
sir.
think the questions is here is tool to practice Verilog on Ubuntu Linux. I have also posted the same question in the form. I don't know whether you got the answer in the forum or not, but the answer is that very simple, that you have basically this iVerilog, right, which is free, which you can actually install in your Linux system, and iVerilog, you can actually check the correctness of your code. You can actually simulate your Verilog code, and it's a good thing you can use also. Okay, so iVerilog is the answer to your question.
Sure, sir.
Um, and in addition to that, you want to if you want to use any commercial tool, there is C2S program, right? C2S program of government, and it's basically, if you are from a engineering college, this chip to startup is basically a program through which your college can be a member of this program. It's a free. Then with this you can access any EDA tool, right, from Synopsys, Cadence, anywhere. So I think it's a very important initiative by government of India. And if your institute is not still part of this part of this program yet, so you can actually you request your institute to become a part of this program, and then you can use any of the EDA tool, right? So that is one thing. And there is also one thing called EDA Playground. So this EDA Playground is as an online browser-based system where you can actually use you can actually write Verilog code, simulate synthesis. You can use the commercial tools as well here, right? I think there are some limited access, but this is another area where sometime when you're learning something, you're not even developing something very seriously, just for learning from a course perspective and all. This can be also a good platform, right? So this will take some time to load, but I think this is another platform through which you can actually use the commercial tools as well. Okay. So this, I think, answer Deep Shankar's question. Uh,
Thank you, sir. Actually, I got the thing
yeah,
correctness.
yeah, thank you. Yeah.
And sir, there is
I'll
one more question about the FPGA, sir. Do you recommend using FPGAs to simulate hardware, like
see, essentially, if you have your design and you want to check the correctness, the simulation, if you just simulate that simulator, you'll see whether your Verilog code is correct or not, right? With some test bench. So that's the kind of functional correctness. Now, uh, once you use this code, whether the code is efficient or not, right? So in the sense, what will be my area in the target platform? Whether what will be my latency? What will be the delay of the circuit? This you will not measure when you simulate, right? Simulation will only check whether your code is correct or not, right? So in that sense, when you want to check the performance of your code, you need to synthesize it. So if you want to synthesize, there are two options. One is basically either you synthesize this the same thing for FPGA, or you synthesize this for ASIC. So if you want to synthesize for FPGA, you use mostly Xilinx, AMD Xilinx tool, Vivado, VTs, and then all other their tools. So that will actually synthesize your Verilog for a FPGA platform. And then you'll get your number of, delay number, power, timing, everything from the tool, right? So that actually give you whether your code is good. So suppose you want to develop a tool, so there is a code, Verilog design, which you want to run it in 200 megahertz. And then when you run there, you see that it's not able to meet 200 megahertz, it's only giving 170, 180 megahertz. Then that means you need some modification in your design so that you can actually improve the delay of the circuit and hence the clock, right? So in that time, you can actually identify the critical paths of your design, try to do some rework there, some optimization, and then you resynthesize again, and then you get your target clock, right? This is just one example. So from a academic perspective, we usually use FPGA because it's easy to use. You don't need to dump into FPGA all the designs. Just simulating and get the PNR, you get most of the numbers correctly, right? If you dump into FPGA as a bit stream and then you simulate, you'll get the actual number, but that needs some extra thing because you have to now connect your PC with the FPGA and your input will go from the PC to the FPGA board and output come back to PC and so on, right? So all those need some extra thing. If you are very much interested, you can do that. But just simulating with some Xilinx FPGA synthesis tool will be good enough. This is for FPGA. And now for ASIC, you also have tool like from Synopsys Design Compiler. Cadence also has the similar tool. So you can actually use those tools to simulate for ASIC. Now, if you ask me the question, what is the difference between ASIC and FPGA? I think many of the students knows it. Just for completeness. Uh, the FPGA has a fixed hardware, right? It has basically the lookup table, which is basically combinational blocks. It has DSP, which is basically an efficient version of the multiplier. You also have RAM, block RAM for the storing the array of data, which is basically memory. So when you synthesize your design for FPGA, effectively your all combinational circuit will be mapped to the LUTs. Your most of the multiplier will be mapped to the DSPs. Your lot of arrays will be mapped to your this block RAM, right? So this is the kind of mapping. So you will get your performance in terms of the LUTs, FPGA, and DSPs, right? So DSPs and block RAMs. On the other hand, in ASIC, you don't have any dedicated hardware, right? So when basically what I'm trying to say is that in FPGA board, when you purchase FPGA board, its hardware is fixed. It may have 10,000 LUTs, 100 DSP, 200 block RAM. That is fixed. The version you purchase. More money you put, you get a bigger FPGA. So now when you try to synthesize your design, you are reusing this, right? So this is reconfigurable. So you can actually configure this LUT based on your requirement. You can configure this DSP based on your requirement, right? So effectively the resource is given and you are effectively mapping your design into this resource and you're using there. As long as your design size is less than the area available, it will work there. But if you are having say 1,000 LUT, but you need 10,000, it will not work. On the other hand, ASIC, there is no target fixed resource, right? You are synthesizing your own design and you have given a technology library. It may be NAN45. So it basically, this library has a different set of gates and all. You have to use them. So what synthesis tool does, he rewrite your every Verilog code in terms of the library nodes that you have there, right? And then your design will be kind of rewritten in terms of the technology library nodes. And then this will be fabricated, right? So you basically don't get any chip there unless you do the fabrication and you get the physical chip. So all the chips that you have inside your computer, mobile, any other device, these are basically ASIC chip. But FPGA is a fix and it is not mass for mass production. For prototyping, or say you want to put something into satellite, right? Or you something you want to put into the mission that goes to ISRO, send it to moon. So, or you try to put in something into very some radar. All those kind of cases where you are when you don't need a mass scale. Say, I don't need 1 crore number of chip, just like mobile. There we use FPGA because FPGA is very easy to get. You don't need to do the fabrication anything. And specifically for research, like researcher like you and me, who actually try to generate hardware, FPGA is a good research because you don't need to do the fabrication. That is a costly affair and you don't have access all the time. So what we do usually we synthesize the thing, design into the FPGA board and we measure the performance and see whether we are able to meet certain goal or not, right? So this is what is the overall story, right? So uh, I mean, as an academic researcher, you are fine to use FPGA to
So
give the
basically, I'm using a Xilinx Spartan 6 FPGA board with IC ID, and I'm
Mhm.
connecting this board with my PC using a JTAG adapter that is provided by the company as well. And I'm like getting the outputs in a real cathode ray, sorry, not a real oscilloscope, which is a 4-channel oscilloscope to get the
Mhm.
exact like configuration. That is
Yeah, yeah.
basically what I
Mhm.
use
Okay.
for simulating actual hardware. So the only
Yeah,
thing
that's
I
great.
was
Mhm. Mhm.
so that is what is the configuration I'm going for.
Yeah, yeah, I think that is good. So you are already quite advanced in this direction. So that's good. So at least you know how to basically connect with PCs and the SoCs is simulation that, right?
Yes, sir. So
Okay, good. So this is the EDA platform interface. So if you log in here, you will have all the tool you will see. You can actually select Verilog, VHDL, System Verilog. So it's a good environment. And for fun, you can use this EDA playground as well. Okay. Uh, so I'll now move on to the other questions in the forum. I think the next question coming from Janardhan does not have any questions essentially. Then the next guy, I think this is Muhammad Safiullah, and he has so many questions. Let me go one by one. Uh, so he has, I think, mentioned certain project here. The first one is hardware optimization, quantized logic. In my project, I'm implementing a hardware accelerator CNN. Since the Tang Nano 9K has limited resources, that's the exact thing I was talking about, 8640 LUTs. What are the most effective Verilog coding technique to quantize or optimize my Mac unit to save area without losing accuracy? So the question is, see, it's nothing to do with Verilog, right? So there are two things you can do here. One thing is the quantize, as you mentioned. So let's say your weights and biases are 16-bit. So if you now have everything 16-bit, so if you have an adder, it will be 16-bit adder. If you have a multiplier, this will be 16-bit multiplier. Now let's say I quantize it to 4-bit. And obviously, if you quantize the value into 4-bit, your accuracy will be impacted, right? So there are a lot of research actually being done here. It's not that probably will quantize the entire network because that might probably reduce the accuracy of your design. So sometimes people what it does, they people it identify what are the most important layer in my implementation, and usually from our perspective, we have seen that it may be the lower layer or the earlier layer. So you basically based on your implementation, I mean application, you can see which layer has more impact by changing the weights there. And if you see that your accuracy dropping drastically, that means that layer has more importance, right? So the layer which is less important, you can use more quantization, right? So 4-bit. And for the layer which is more important, you can use 8-bit, right? Or maybe 12 bits instead of 16-bit. So if you do this way, it's not a fixed quantization. Rather, you are basically doing a measured quantization based on the importance of that layer. You can actually get good area down. I mean, you can reduce your area, but without much impacting on the accuracy. I think this is it's an important problem. That is one direction, quantization. The other one is basically called approximation. So you don't need to probably need a actual adder. So there are a lot of research happening on approximation architecture, right? For multiplier adder. So to give an example, let's say I'm doing multiplication. So say I'm doing multiplication, right? So I'm basically multiplying the input with the weights. So the result, finally, what we do, if the value is beyond some threshold, then I'll do something. If it is less than threshold, I'll do something, right? So I don't need essentially the actual multiplication result. So I can actually use some approximate multiplier. I mean, just giving a very simple example. You think about that I have two 8-bit number and I just use the MSB. So let's give a simple example on adder set. So I'm basically doing 8-bit addition. I have two 8-bit number and I'm doing the addition of them. So one 8-bit number can be 0 to 255, right? And results can be um, uh, up to 512, right? So you can have actually result up to 511, basically 9 bits. So now let's say what I did, I decided that I'll only do 4-bit addition, all the 4-bit as a MSBs, and I'll assume that the LSBs as zeros. So then what will happen? You are effectively out of this 512, 4-bit only consider 16 numbers, right? So you effectively your value will be not accurate, but there'll be some approximation which may be maximum 16 value less or addition. I mean within the 16 possible value which is from the actual results, right? So your result may be 500, but you are getting 485. I'm just giving an example. So many a time, even if you, so now you only need a 4-bit adder. I don't need an 8-bit adder. So I'm basically saving the entire area for 4 bits, right? I'm just giving an example. So with this, my addition result is not exactly what I want, but this is good enough because I'm doing the addition of the LSBs and then I padded the 0 at the LSBs. So I'll get the result, right? So, and the result will be very close. So what I'm trying to say is that maybe this approximation also is good enough because you don't need the actual value. You just need the value, which is how close is that, whether it's a very high compared to some threshold and all, right? So this kind of technique you can consider to map it to the target architecture. I think that answers your first questions. Then you have another question which is called practical implementation. When writing Verilog code for real-time image processing, how do you suggest managing the memory buffer for pixel data efficiency within the FPGA block RAM? Okay, so very interesting question again. I'll answer, just give me a minute. Yeah, it's a very important question. So what he's saying that you want to implement an image processing application in FPGA using Verilog code. And now for image processing means you need to have the image, which is kind of a 2D matrix, with a 2D array, and that data has to be stored in image, I mean, in some block RAM, right? So, and then you basically do the computation by reading the data from the memory and do something, right? So that is how you're going to implement whatever the image processing application you're doing, whether it's kind of doing some kind of image processing like adding the age, or maybe you try to do the image enhancement and so on, right? Uh, so here, the primary thing that you need to focus is that the main problem when you basically map something into block RAM has a fixed number of port, right? It has either one port or two port, single port or dual port memory. What does this mean? It means effectively you can read either one or two value, read or write from the memory. So now you basically, but when you write, when you have an array in C, you can access all of them, right? You can actually access 4 elements from the array and do something, right? So we write those kind of thing in C. But in hardware, if you have to access four data from that memory, you need, if it's a single port, you need 4 clock, right? So what is very obvious in C, where I can say I do AI plus 1 plus AI plus A into, sorry, say AI plus 1, AI plus 2, and AI plus 3. So these four data I want to read in 1 clock. In C, I just write AI plus 1 plus AI plus 2 plus AI plus 3. Right? But in hardware, even if you have this expression, you cannot do it in 1 clock. If you have a single port memory, you need 4 clocks. So the main bottleneck comes when you have the block RAM based memory, you can only read a very limited number of data from there, right? So what is the good deal here is you try to, if you are reading the same element multiple time, don't do that, right? So you basically read once and store in some local register so that you basically save 1 clock reading from the element from that memory. So this is one of the strategy whenever you are using block RAM, that you try to rewrite your expression such that I'm basically avoiding rereading. So I don't, if I want say A5, I'll read only once from the memory. I'll not read multiple times. If I need A5 multiple times, I'll read once and store in my local register so that I don't need to spend another clock to read the element again, right? So stored locally is the one of the good strategy. The other strategy is that you can actually rethink about the computer. Many times we just read unnecessary, right? So you probably don't need to read that every time. So just to give an example, let's say, so I'll just give an example. Let's say you have, say you basically have, I'm just giving a C code, but you can write equivalent. If you have, suppose you are doing AI equal to, say some equal to, say AI plus AI plus 1 plus AI plus 2. Right? So something you are doing like this. Say sum I. Now you see here for sum 0, I'm reading the location. For sum 0, I'm reading the location. 0, 1, and 2, right, of A. Then for sum 1, I am reading the location which is 1, 2, and 3, right? For the sum second location, I am reading the memory which is 2, 3, and 4, right? So you can see here, effectively for new location, I have to just need one of the value, right? So for when I know that I have read 0, 1, 2, for sum 1, I don't need to read 1, 2 again. I just need to need 1, 3. So what I'll do, I just store this 1, 2 locally, and then I'm going to use it for the next iteration, right? Just to give an example, what you do here. So I can rewrite this program like this at T1, say y1 equal to a0, okay, and then y2 equal to a1, right? So this I'll do before the loop, and then when I do this loop, what I'll do, I'll not read anymore all elements. So what I'll do, only sum I equal to sum I equal to y0, sorry, y1 plus y2 plus only a3, right? So sorry, this is basically I plus 2. Okay, so this is the only value I'll read. And then what I'll do, I'll just move these values, right? So what I'll do is I'll make y1 equal to y2. So that means now a1 moves there, right? And then y2 equal to sorry. So basically, I'll not even do that. So what I'll do is I'll read y3 equal to this a equal to a plus 2. And this is I'll put y3. Okay, and then I'll do y2 equal to y3. So if you do this, what is happening here? So you see, I'm just reading only one element at a clock, right? So when I'm just only reading one element, and then I'm doing the summation, and then just shifting the value. So y2 to y1, y3 to y2, and then a y3 I'll read again. So the same operation here, I need to, for every operation, I need to read 3 location of the array. So it needs 3 clock. Now if this loop is 10 times, so 30 clocks. Now every clock I'm doing only one read, so basically I need 10 clocks. So I save 20 clocks just to for the memory read, right? So this is what I try to mean for doing this. Okay, so I'll move on. I think I have answered your these questions. Then the industry readiness as an EC student graduating under an university in R21 regulation. I don't know what is R21. I want to know how much emphasis should I place on learning system Verilog assertions versus traditional Verilog test bench to be industry ready. I would suggest you must learn system Verilog assertion because industry everybody use system Verilog assertion. So effectively, test bench is good, but please learn system Verilog. That's very important for the industry.
Hello.
Yeah. Any questions?
Sir, is there any importance in the UDPs at Verilog HDL?
Yeah, Verilog you must know, right? So you can make your design in Verilog. There is no problem. Okay. But usually people write the assertions in system Verilog, and then they in the simulation framework, people mostly use system Verilog assertions. And if you know Verilog, learning system Verilog is not that big deal, right? You must know Verilog as well. But system
Sorry, sir,
Verilog
is there any importance in the user-defined primitives at Verilog HDL level?
user-defined primitives?
User-defined primitives.
I don't understand what do you mean by user-defined primitive. So you have to develop modules, right? When you make a bigger design, you need to, yeah. So you know how to develop your own module, how to integrate them into SOC. That's very important. That's a design. That is basically your knowledge about how to make a big design, right? So that is very much needed. But once you have a big design, you want to make sure, you want to check whether there is any bug in your implementation, right? So that is where the system Verilog assertion and those things come. So you need to know that as well. Okay. I think there is one question from Vijay Kumar, I guess. Sir, I'm still studying the diploma second in IC domain. is there any use of this course in future of Verilog domain regarding this job and placement? See, I think this is anybody in the EC department, they must know digital design. So this course is quite important for you, any EC graduate, I would say. And somebody is working in EC electronics electronics branch, they must know some HDL, hardware description language, right? And Verilog is one of the popular. So yeah, so that way this course is quite useful for you. Okay. And then the next question which I ask is, sir, could you explain the difference between uh, the synthesis and simulation in Verilog? So I hope you got the answer to this question. So what I was trying to mean that simulation means you have the implementation, you have a test bench, you are running this design for the input coming from the test bench and check whether your design has any functional bug. That is simulation. And once your simulation is done, that means your design is correct, you throw away your test bench, right? You take this, and this is in Verilog in high level, in register transfer level. But when you try to map into, say, you want to build a chip from that, which is, suppose you have done an image compressor and you want to put that into your mobile devices as a chip. Then what you have to do, you have to build the physical chip for that. So for that, you need synthesis tool, right? So what it will take, it will take your compressor design in Verilog, and it has step like logic synthesis, physical synthesis. It will do clock tree synthesis, all the PNR, everything it does, and then it will give you a layout, right? And this layout is kind of a transistor level design, which can be, there's a fabrication lab which can take this and you can actually build the actual IC integrated chip based on your connections and everything, right? Then you get the physical chip. So synthesis is basically bringing your high level behavioral description into the layout, and then finally you do the fabricate to get your chip, right? So that is how you can differentiate between simulation and synthesis. Okay, thank you. I'll see if there are any questions here. No, I don't see any questions in YouTube. So I'll go on and explain the questions that I have in this chat. And then the last question Muhammad Safiullah is, he's a very serious student, looks like. Debugging and verification. Debugging timing issues in a CNN pipeline can be difficult, yes. What is the best practice for using static timing analysis report to find bottleneck in my Verilog code before I flash it to the hardware? I think it's a very important question, and it is where the expertise come into picture. Um, because your static timing analysis will come in terms of the get level design, and probably you have a Verilog which is in register transfer level, right? So they are in two different abstraction level. So usually what people does in industry or the common practice is that you open the report, the timing report, and identify critical paths, right? What are the path is critical? And then you try to get the map of this path into your input design and see what kind of optimization or what kind of changes you can do there so that that path the delay become less. And there are two things you can do here. You can manually change that path. You want to do some optimization there, putting a pipeline stage in between, right? Those things you can do on your own, or you can actually use some pragma of the synthesis tool. They actually do many things. They probably you can actually ask the tool to put a register there, or you try to do a more ultra optimize in this path and so on. There are things you can do so that in the next synthesis you can actually improve the timing of that particular path, right? So this is basically comes with expertise. But I'll also kind of throw some light on this. What people are trying nowadays is basically try to people use the large language model like ChatGPT, DeepSeek, right, or Gemini. What people do is try to create a agentic framework where they basically give the static timing report to the ChatGPT and also give the design and say that suggest me what I should do, right? And if this particular tool over time learn what is the kind of common, you can actually give some hints that if you have this, this is what pipelining, this is retiming and all those things. You can actually give certain documents and all. I think most of the tool are already trained on those kind of thing. And people in the industry nowadays trying to see how agentic AI can help in this kind of analysis, critical path analysis and all. So it can be a good idea for you to uh, 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 actually open and try this kind of agentic framework, right? Whether you are getting any hint, it can actually give you suggestion. Oh, do this, do that, and all, right? So some suggestion it give, you do that. So if you can close in say 10 iteration manually, if with this process you can close this in 5 iteration, that means you get a lot of benefits, right? And I can tell you the industry is now trying very hard to bringing this kind of agentic AI framework to kind of correlate this bug report with the actual design and try to get the solution through chat LLM and ChatGPT. Okay. I hope I have answered your questions. No question from Suchi Bajaj. Karuna Karan he has problem with encoder decoder. Probably I'll explain them at the end, uh, which I already have the video. I think if you listen the video carefully, it should clear your doubts. Then Asadullah Siddiqui has a questions like, is there NPTEL internship associated with this course? Yes. Last year, I think 6 students came from this course who have done well in this course. I usually take intern through this course. And this year also, there are 5 students got selected, and they did the internship online because of some short time and something. But I prefer people come to the campus to IIT Guwahati and stay in hostel, work from my lab. So yes, there are internship opportunity. Then Uday Teja has questions. What skills are most important to get an internship in VLSI dozen? Is very difficult to answer because internship, where are you looking for, is industry or academics? That is also matter, right? So whether you are looking for industry experience, internship, um, or academic internship. So for academic internship, unfortunately, we usually get a lot of email, right? I feel bad, but sometimes it's very hard for me to respond all questions individually or all emails. So what I usually do, I usually take students through my courses. I have 2 courses running in 2 semesters, and then the third course will be running. So I'll have 3 courses now in NPTEL. And I usually prefer a student from NPTEL platform because here the serious student who did well in my course are coming, right? So they're already shown that they're good student, right? And sometime, if some of your professor who knows me and all, they are recommending me that he is a very good student, we also select, right? Industry, I don't know how the industry internship works. For IIT, they come for internship exams and all, right? So yeah, for IIT student here, they basically goes through the placement process in the internship. But one suggestion I have for you is you decide your career path first, right? So whether you want to go to industry or academics. If you want to go to industry, try to do something. Try to improve your career so that profile so that it is good for industry, right? Um, but if you want to go to academics, higher studies, say you want to do PhDs and all, then try to get an academic internship and do some research-oriented projects, right? So there is a substantial difference between an internship in industry versus academic, right? Based on your career goal, you please take a decision. Okay. I think I have another questions from here from Vijay. Sir, what coding style prevent inference of block RAM in FPGA? It's a difficult questions. So what I'd suggest, so if you probably do not follow, see, I mentioned that the memory has a limited number of port, right? The block RAM and all. So now if you do not follow, say, if you are using too many reads, right? And then synthesis tool found that if I move it to the block RAM, it will take too much of time. Hence, but I found the memory is small, so I put it into register so that I don't have this problem of memory access through the port, right? So if you have too many memory access, then sometimes synthesis tool map those block RAM into register instead of the block RAM, right? So this is one of the common problem. And then there is also problem like read before write and write before read, right? So you are basically reading some element from an array and then same clock you are going to write back, right? So those kind of cases, there are some restriction. I mean, when you can read and write, so you have to go into the detailed documentation from the design tool, and you have to see, are you following all the rules correctly, so that I mean, if you follow all the guidelines of what are the scenarios supported by the block RAM access, if your code follows that, then your code will be mapped to block RAM, right? The problem is if a small array, if you map it to register, there is no problem because it's okay. But if you have a very big array and because of your bad coding, it map into block register, then what happened? Your most of the register will be occupied, right? So then you're not able to synthesize the other part of the design. So you need to be little bit. So this is very serious questions and lot of internal things you need to know, how the block RAM getting inferred, what are the things is not allowed in block RAM, and then how can I modify more code and um, to do that, right? So this is what to answer your questions. I think there is one more question from Vijay. Let me check from YouTube also. Is there any other questions there? I think in YouTube there is no much question, which is good for me. So I'll answer Vijay question first. The question is that what is the difference between Moore FSM and Miller FSM? So in one case, your next state depends only on the present state. And in one case, it depends on the present state and input, right? So you can see the definition from book and then you can study accordingly, right? So it's all about design style. How do you effectively develop your controller FSM? Okay, let me see the other questions from the board. And then the last question from Deep Sankarcha, I think I have already answered his question. What are the tool to need for practice Verilog, Verilog, and this EDA Playground and C2S? And then what are the best FPGA we can get to practice hardware design? So for practicing, you don't need any FPGA, but when you try to implement something in physically, you need FPGA board. But depends on your application. If you are applying, I mean, if you are creating a bigger hardware like for CNN model and all, probably you need a bigger board. But I think if if you are from engineering college, most of the engineering college have their own FPGA board, right? So you don't need to purchase anything. So based on your application, if you open any FPGA board, it will basically say how many, if it's data set, if you open, it will say how many LUTs are there, how many block RAM is there, how many BRAM is there, and how many DSPs are there. So based on your application, you choose which is basically can fit in your design, right? So that is the correct answer to your question.
Basically, I'm a hobbyist. So basically, I don't study in engineering college. I'm just like a learner. I actually do. I'm a freelance computer developer, and I have a company as well, a startup. But I do this hardware design just for learning and exploring new ways to do that. And for this, I think like I have the hardware, but like I just had the Xilinx Spartan 6, the old one.
That is good enough. Spartan 6, right? Which is very good. I mean, I think good enough for any kind of practical design you'll do as a student. So that way, I think Spartan 6 is good enough. Yeah.
I implemented very basic circuits. Basically, like I implemented the old MOS 6502 chip, basically, I think, and old 8-bit chips. Basically, I implemented those things. But like sometimes the design doesn't work. You have to do a lot of debugging. So I'm just going through this course to understand all this stuff, because like earlier when I learned these things, I had to do like in a very in an improvised manner, because I'm just a BSc in computer applications. I don't have much exposure to hardware, but I had to go through different courses on Udemy and all that to just understand these things in a very like improvised manner. But this course gives me a formal introduction and a proper roadmap to understand the hardware design concepts. So thanks a lot for providing this course. So that's also something which I have to just share with you.
Okay. Thank you, Divsinkar. Yeah. So I think then Spartan 6 is more than enough for your purpose. Yeah. Okay, I think I'm done with all the questions. I think encoder decoder is something is already taught in the class, so I'll just quickly go through because there is a questions. So basically, the encoder and decoder is a combination block which just as the name suggests, encoder, right? So you can have basically 2 to the power n possible input, and then you have basically n output, right? And effectively, it's basically saying that if you have three inputs, there are eight possible output, right? So you can expect in a normal encoder only one of the input is one, right? So and basically, if it is just a D7 bit one, basically that means you're actually say 7, right? So it's basically 1 1 1. So in a normal scenario, if you have these cases, so you can actually construct this truth table and then you can implement X, Y, and Z based on the number of one, right? So this is basically this. It's very simple. But the problem with this encoder is that if in some cases say both D0 and 1 both came, then what will you do? So both have been, then your output will be inconsistent, right? So you will not see that whether if say you are expecting say D1 came, so you are expecting 0 0 1 to be the output, but it's not happening, right? So in this case, you need, so in general, the assumption of this that at most one of the one bit will happen, one, but if more than one of the input is one, then I don't know what is the output. The output will be inconsistent, right? So to handle that, this is the priority encoder where you basically assume that if I have this P1 is 1, I'll ignore the previous bits, right? So for example, if I want P6, which is basically 6, for that I'll ignore all the previous bit. Even if there is 1, I don't care. So this is a don't care scenario, right? So now if you consider this scenario and if you simplify this, you'll get this is the circuit expression. So if you do this, now there is no problem. You'll get, if you give this bit 1, it will ignore all these bits and it will actually give a P6, right? 1 0 0 1 1 0 output, right? This is the encoder. And then I have shown that how you implement this and all. Then I saw the Verilog, and the decoder is the opposite, right? So it's basically if you give 0 0, it will basically, if it is 0 0, this bit will be 1. If it is 0 1, then this will be 1. If it is 1 0, then this will be, this output will be 1 and so on, right? So, so this is a simple decoder, and you can easily extend for 3 to 8. So it has n input and 2 to the power n output, and one of the output will be only one, right? Based on the input value, right? And you can actually construct this truth table and you can actually make this, right? So it's basically D0 means 0 0 0. So you basically connect 0 0 0 to this, to D0 and so on. Then what I have shown is effectively, if you want to make a 4 to 16 decoder, you can actually create 16 such AND gate. But what I have seen, but those are actually, each of the AND gate has 4 input, right? So one 4 input AND gate is effectively means there are two input AND gate, right? So your area cost will be high. So what I have shown next that how do I can use 3 to 8 encoder with the enable line to connect this enable so that either this part of the encoder is active or this part of encoder that is active, and then how you can develop that with 2 3 to 8 encoder, right? So that way you can actually calculate what is the saving and all. And then I have shown that you want to develop this 4 to 16 decoder, but you have only 2 to 4 decoder, right? So what you have done, you basically have 2 to 4 decoder, it will give 4 output. And then you can combine this 4 and 4 output to this AND gate, and then you can actually, this output is 0 to 16, right? So this way you can combine them and create a bigger circuit, right? This is what I have shown. And then the decimal encoder where your output only 0 to 10, 0 to 9, not 16 and all. And then here you have some don't care scenario. You can combine them to get a some optimized version, right? I think this is what I have told in the class. Okay. So I think one more question is from Vijay. Next question he has is how does Verilog infer D flip-flop from always passage clock, right? So this is Verilog does not infer, the synthesis tool infers, right? So it basically, whenever it says that there is a always passage of clock, it's basically age trigger flip-flop, right? So it is basically at the positive edge of the clock, you are doing something. So it will infer the corresponding flip-flop there in your ASIC technology library. It may be some D flip-flop or some other flip-flop maybe, right? What Verilog mistakes caused by the student who lost marks in NPTEL any exam regarding the Verilog? I think this is because this NPTEL exams are online and kind of MCQ type. Uh, you don't have to write the entire Verilog code, right, all the time. So I think if you know the basic concepts, basic syntax of Verilog, you should be able to answer questions in the online platform. Okay. Okay, I think good. Vijay has so many questions that I like. And Deep Sankar as well. He has also quite few questions, which I enjoyed. I think I'm also end of this session. It's a very quite active session for me. I have so many questions. I'm quite excited that students are following the courses very seriously, asking very relevant questions. And I wish all of them all the best. And then hopefully we'll meet again in the next live session. I think within a month, by end of March, I will have another live session, and we'll talk further. Right, till then, thank you. Looking forward to the next live session. Thank you very much.
Thank you, sir. Goodbye, sir.
Goodbye. Yeah.